not much left to go. 24.3, stereoisomerism in complex ions. So I'm going to go through that with you now. So I'm going to share my screen and we will get started. Okay, so so homework is as usual, support as usual. So ligands that we have come across so far. Right, so we've got chloride, that becomes named chloro. Cyanide, Cn minus, that's cyanide, thiocyanate or thiocyano when you're naming the compound. Hydroxide becomes hydroxo, O2 becomes oxo, water is aqua, and ammonia, or which its lone pair is going to become part of a ligand, is amine. Yeah, amine. Yeah, be careful, it's not amine, it's amine, it's double M. Okay, so that's the difference there. Okay, so a quick revision point. Okay, so the title of this lesson is Stereoisomerism, and you think, yes, that reminds me, I'll go back to thinking about butene and in fact it can be cis and trans. Okay, so stereoisomer, okay, these are geometric stereoisomers, so you can stop the video and draw out and label cis and butene and trans butene now. Okay, so if you stop and then carry on when you're ready. Okay, so here we go. We have got on the left here, we have got trans. Now it's labeled trans because this is a special case, cis and trans, when we could have E and Z isomerism, but this is cis and trans when we've got the hydrogens are on opposite sides of the double bond. So trans is opposite. Cis, they're on the same side of the double bond. Okay. Okay, so what we're going to look at here is the fact that in the transition metal complex, we could have cis and trans isomerism. Okay, we'll look at a specific chemical called platin, and cisplatin is an anti-cancer drug. Okay, it will bind to DNA. Notice it's cisplatin, so the actual stereoisomerism is important in its anti-cancer drug effect. And we obviously have a quick look at how that works, but then we need to be able to look at cis and trans isomerism and optical isomerism in the transition metal element complexes. Okay, so we've got stereoisomers. It's the same structural formula, but a different arrangement of atoms in space. Okay, so using the molly-mod kits, we're going to make an octahedral complex, and we'll use oxygen to represent water, and chlorine for, or green for chlorine. Okay, how can you arrange them differently to form a different isomer? Can you see any cis or trans arrangement? Okay, draw in 3D what you make. Okay, so I am going to stop sharing my screen. Okay, and you should be able to see me. Okay, and then I'm going to show you what is meant by that. Okay, so here is a molecule. That's good. The background doesn't work very well with that. Let's turn off the background, if I can do that whilst we're still recording. Video settings, more meeting options, different background. Unless I hold it in front of me like this. Okay, if I hold it in front of me like this, it's going to work, I think. Okay, so actually I should try and, yeah, that's okay, background is off. Right, okay, my molecule works and I can hold it over here and it's nice and clear. Right, so here is my molecule. Okay, so we're using the red ones to represent water. Okay, there, yeah, okay, so there's a red one there. Okay, that represents the water, and the green one represents chlorine. The reason we're using the red is because we don't have any reds. I've got 3 holes in, because obviously normally oxygen makes 2 bonds, which you would need to do to make water. But then what we're trying to show is the lone pair joining on as well. So we need 4 of the oxygens on there. Okay, so hopefully you can imagine this as the molecule. Okay, and you can see that the oxygens have taken a square planar effect here. So that actually is interesting because there could be another isomer of it. I could swap a chlorine and a water around, and we get this one. Okay, And the greens look as though they're on the same side as opposed to opposite sides to each other. So they're on the same side, they're in the planar formation, and so that is our cis variation. And therefore, if I switch it back, we've now got our trans version. You can see that the two chlorines are opposite each other. Okay, so that's trans across from each other. So we can see cis and trans here like that. So in stereoisomerism, we do use the cis and trans nomenclature rather than EZ or anything silly like that, because it's not a double bond. EZ is only double bond. Cis and trans can be used in stereoisomers. So this is an octahedral complex. We've got 4 water molecules, or supposedly 4 water molecules. It's the lone pair of the oxygen that is donating electrons to form the covalent bond here, and then we've got a chloride ion. So that's a chloride ion, yeah, and we can imagine it's got the bond attached because it's got the 2 electrons. It's Cl minus and going in on there on the metal. Now we're using this yellow molymod for the metal because it's got 6 coordination on it. Okay, so if we draw that out, you would draw them like this. Now remember, we put square brackets around a complex, and this is the generic formula of it. So we've got MA, so A is one of our ligands, and there's 4 of them. B2, so there's 2 of our ligands, and you can see that we have our cis or trans ones. Yeah, okay. Now we can make a slight modification to that. If I remove, oh, I'm not showing you that, am I? So let's just share that. So first, let's go back and quickly share that. Okay, so you can see here we've got M for our metal, which is the red one, or in my case, it's the yellow atom in the middle. MA is, in this case, it's the red, which is supposed to be water. So there's 4 of those. B2 is the chlorine, okay? And therefore we get cis and trans. So that's what I showed you here. The trans is where the 2 are opposite each other, and the cis is where they're next to each other, in the planar part of this molecule. Notice that we've got square brackets around it because it's still a complex. And the N plus is, well, depends on what the charge on the ion in the middle is. So chloride is -1 and -1, so that makes -2. So if we had, say chromium 3 plus, okay, then this would be +1 overall, because the chromium will be 3 plus, the -1 makes 1 plus overall. Water is polar but does not have a charge, so it would not affect the ionic charge here. Okay, so down below we now switched to having a 3 and 3. Okay, so we've got a 3 and 3 combination, and you'll see that they're called trans. Okay, where we've got 2 across from each other. Okay, but they're all in the plane. They're all in the same plane. Okay, 2 across from each other and 1 in the 90 degrees. And here we've got cis, which is where they're not in the plane with each other. We've got them at the sort of this angle here. So there's 3 here. Now they are called tris or trans or cis, but we can, so these are all at 90 degrees to each other. Yes, they're all at 90 degrees to each other. Here we've got 90 and a 180. Yeah. Now the other, there is another terminology for this. It's called MER and FAC, or FAC. It's because they're in the same face. Okay, whereas these are not in the same face. So let's show you that on my molecules. So taking those off. So just make sure you can see so you can see this. So this is the trans or MER form, okay? And you can see that I've got the 2 which are 180 degrees to each other, and they're both at 90 degrees to the other one, but they're all in the same plane. Yeah, they're all in the same plane. Now if I switch it around like this, they're at 90 degrees to each other. They're not all in the same plane, okay? That is the cis, okay? They're in the same face, okay? So if we put, if you imagine there's a face, this would be a triangular face of the molecule. If you imagine a triangle with the points there, and there, they would be there in, that's cis, but it's also called face, okay, or face, yeah, because they're in the face form. And you can see these are cis because they're all next to each other. Whereas if I do put it back to that, they're not all next to each other. You know, this one is next to that one and it's next to that one, but this one and this one are apart by 180. Okay, let's share screen again. Okay, so move on. So now, right, we can now have a look at the square planar arrangement. So let's put those onto here. Okay, so we can have a square planar arrangement. I'll demonstrate that. Can we get different isomers for this? Can you make cis and trans isomers? I think yes, we can. What do you think this could be something called cisplatin? Okay, draw in 3D what you make. Okay, so we'll have a look at that. Yeah, so what do you reckon the metal is in cisplatin? Okay, it's it's platinum, obviously. Yeah, anyway, let me demonstrate the possibilities here. Okay, so here it's got 2 nitrogens, yeah, and 2 chlorines here. Okay, so that is one formation of it. Okay, and I think you can probably guess that that's the cis version. And then if I do this, that's the other version, and that's the trans version. And you can see this one has sort of, it's got vertical and horizontal symmetry. Okay, so that's interesting. Whereas this one does not, it has vertical symmetry, but it doesn't have horizontal symmetry. It's not symmetrical that way. It is symmetrical that way, okay, but not that way. So that's going to be interesting in terms of how it would react with stuff. So we're imagining that the yellow one is the platinum. Okay, there's our 2 chlorines and there's our Ns, which come from the molecule, well, yeah, the molecule that bonds here, the ligand. So let us share the screen again and move on. Okay, so this is it in square planar. So we've got the 2 forms. So at the end is from ammonia, yeah. Okay, so this we've got the trans, okay, across from each other, cis, okay, on the same next to each other. Okay, so this is only symmetrical that way. This is symmetrical that way and that way. Okay, so there's a little video there that you can watch. I'll try and see if I can embed that into this video, which talks about cisplatin. Okay. Okay, so the metal could be, so nickel, palladium and platinum will also form this square planar formation. So trans and cis, okay? So it is the cis version that is the anti-cancer drug, okay? So it's got a 4-coordinate complex, yeah? So obviously it's 4-coordinate means making 4 bonds, 4 dative bonds, covalent bonds, as a metal, which is, you know, is a bit unusual, new in 6th form or new in A-level chemistry, where we're talking about metals making covalent bonds. Okay, so cisplatin is an anti-cancer drug, square planar, anti-cancer. It binds to the DNA of cancer cells, preventing replication, leading to cell death. Okay, so it's going to, you know, it's actually going to bind to cells that are reproducing quite quickly, and obviously cancer cells are those sort of cells. So it binds to those cells, but it does have unpleasant side effects because it will also bind to other body cells that are replicating faster than normal. Okay, so we need to try and look at how we minimize those side effects. So we can modify the molecules, perhaps. Okay, have lower doses and hopefully fewer side effects. So carboplatin, okay, so doesn't have the chlorine on it, but it has this other bidentate ligand, yeah. So bidentate, it's got 2 oxygens, well, it's got 2 carboxylic acid groups here and here, and the oxygen from the carboxylic acid group can join to the platinum with a covalent bond. Okay, so it's a bidentate ligand. Okay, and that is has fewer side effects. And it must be that this drug, this cisplatin, binds to the DNA because of its shape. And you saw the difference between the trans and the cis version. Okay, so therefore it's the cis version that has this the appropriate shape to fit with DNA for quickly replicating DNA. Okay, so there are here's other examples of trans and cis. Okay, so this is going to be a bidentate ligand, and what's happening here is this is a, well, we can work out what this is. We've got an amine group here. We've got 2 carbons, so it's ethanoic. Yeah, so it's 2-amino ethanoic acid, because this is on carbon number 2. Okay, ethanoic acid is the most important group. Okay, so it's 2-amino ethanoic acid. Now look what's happening here. Because the nitrogen's got a lone pair and the oxygen's got is negative because it's lost the hydrogen, they form covalent bonds with the copper. Okay, here. But you can get 2 arrangements. You can get trans. So here the oxygen is on one side and the other side of the copper, whereas in this version, okay, the oxygen is bound next to each other. And again, okay, that will mean that the shape of the molecule is slightly different. In fact, I probably have got something I can use to model that. Yeah, okay, so I'll take that one off there. I need another one of these. Got another one of these. Yeah. Take that off there. Take this one off. No, I can't. Take the wrong thing apart. No, let's do that for later. Okay, so let's move on. So optical isomers with bidentate ligands. Okay, optical transition metal can show this. It must be a complex with 3 bidentate ligands. Okay, so I can show you that. Did I take it apart? I did take that bit off, but that's okay. I've got that one. And I've also got this one. Right, so I can show you, model this sort of thing going on. Okay, so let's just stop sharing my screen there. Okay, so here is one bidentate ligand. So this is the ligand, it's come along. Okay, these nitrogens would have hydrogens on, but yeah, it's just getting too busy if I try and put those on as well. So here is one bidentate ligand joined on. Here is the other same bidentate ligand joined on, and here is the third bidentate ligand joined on. Okay, so this is that molecule there. Okay, and so we've got the nitrogens here. So here the nitrogens are next to each other. Okay. And this, if I made another copy of this, because there's 3 of them, okay, and you can't get symmetry with 3s, then if I have another, if I made the opposite version of it, it will not sit on top of itself. It cannot sit on top of itself. Right, so that is that one there. Okay, 3 bidentate ligands. Okay, must have 3 bidentate, and then these will have optical isomers. So you'd have to draw pictures of them with a mirror line. Okay. Yes, let's show that again. Okay, so yeah, must have 3 or 2 bidentate and 2 monodentate. So let's take this off. Okay, and put let's put 2 waters on. So we'll use the reds to get oxygen. Okay, so I've got that, which hopefully you can still see. Okay, so we've got 2 bidentate 2. Yeah, okay. So let's yeah, so you should be able to see that. So there, I've replaced the bidentate with 2 oxygens. So I could have that, but I could also have with this, I could also have cis and trans as well. Okay, so I've got cis and trans. So here I've got the 2 reds opposite each other and the 2 bidentates opposite each other. Okay, but if I put it back to the original one that I had, again, this is an optical isomer. Okay, you'd have to have 2 of them. Oh, you'd have to draw the one opposite each itself. Okay. Okay, so yeah, let's show you that on the screen. Okay, so that's here, yeah, and you can see we've got the optical isomers here, as well as cis and trans. So these are both cis. Okay, right. Oxidation states the transition metals. Well, they can change. Okay, so here in this one we've got Ni2 plus. The overall iron is 2 plus. Nickel is 2 plus, is plus 2, because this bidentate ligand doesn't have a charge, so it's not going to change that. So if that's written down as 2 plus, the nickel must be plus 2, the oxidation number plus 2. Okay, in here the iron must be plus 3, because with this ligand here we've got O minus and O minus. So this is ethandioate. It's the ethandioate ion, which has got 2 oxygen minus ions on it, which they become the ligands, and it's bidentate. So there's 3 molecules, so they must be minus 6. The iron, given that the overall charge is 3 minus, the iron must be plus 3. And sometimes complexes can be used to stabilize the less common oxidation numbers of the metals. So remember, previously we looked at the oxidation numbers of the metals and showed the different ones they could have. Okay, so cis can be shown with only monodate, but it's also possible with bidentate. 2 bidentate, 2 monodate shows cis and trans, so I just showed you that. Okay, so that is the cis one. The trans one is going to be, well, how would you do the trans one? Well, you need to put the OH over here and switch that over to there. So this binds around that way, like I showed you with the previous molecule. Okay, actually, I will just show you that again. So here we have it in cis formation. Okay, so there's the cis formation. I switch this over. Okay, there is in transformation. Okay, it's made a transformation. Okay, now this is not going to have optical isomerism, but when we switch it back to cis, it will. Okay, this has to. You can only have a mirror image of this, or you could have a mirror image of this. Yeah, you can't with the trans. Okay, so you would see how you would do that with the diagram here. Okay, oxidation state of chromium. So this is -1. Well, water is 0, so they're not going to affect it. But these two here, these are again ethandioate ions. Okay, but from ethandioic acid. Okay, -1, -1, -1, -1. So that's -4. If this is -1 overall, the chromium must be +3. Okay. So how many total isomers are there for this particular compound? So it's cobalt with ethandioate ions, and ammonia, and a chloride. Make sketches, indicate optical isomers, and draw them as mirror images. So that's a task for you to do. Okay, have a go at it, and when you have had a go at it, come back here, and then I will tell you the answer. Okay, right. So you should have had a go at trying to draw those. Okay, and you should find that there are 3. Okay, and that is it for this session. Okay, so there's a task menu, and obviously if you can come prepared for the lesson, that would be great. And I'll just stop the video if I can get here. Stop recording.